Hi there, my name is Stijn and I'm a master's student at Junhwi University. In this video I will explain how we applied deep reinforcement learning in order to automatically generate API test data. API testing is super important because one small mistake or fault in an API could lead to so many users seeing the effects. Only manual testing is not enough, and automatic testing faces scalability challenges, which I will elaborate on later in this video. Now, although I use API testing as a concrete example to show the benefits of applying reinforcement learning to search-based software testing, I hope that by the end of this video you will also come away with a more general idea and mindset of how you could apply deep reinforcement learning to your own SBST applications, hopefully triggering some interesting new ideas. For this video, I assume that you have experience with search-based software testing, and for brevity I will leave out the details of deep reinforcement learning, but I'll leave some links for your reference in the video's description. And I'll also put some timestamps so that you can easily skip through the different parts of the video. At the time I got started on this project, I was just making myself familiar with API testing and search-based software testing, as these are two of my professor's main research fields. But at the same time, in a completely different context, I was also playing around with reinforcement learning, which is a field where programs learn what to do simply by you telling them if what they did was good or bad, without specifically saying what they should do. So you tell them, hey, you won the game, that's good. But then they have to figure out themselves which moves they should make in order to accomplish that. So I was working on a program that could trade bitcoins for me, because who doesn't want to earn money while sleeping, right? And while I was learning about all of these things, right, API testing, SBST, and reinforcement learning, I naturally had a feeling that reinforcement learning could also be applied as a meta-heuristic search algorithm. Because with SBST we optimize a fitness value, right? In reinforcement learning we basically do the same, but then we call it optimizing accumulated rewards. And as opposed to conventional search algorithms, reinforcement learning has a huge advantage in that it can make use of state information at each point in the test data generation process. Then I saw that researchers from KAIST University in South Korea had actually done something like that before and succeeded, but the way that I envisioned it and the way that I saw this state information being used was very different from them, so I decided that this would be my research topic. Now, before I go into the challenges of API testing that we are trying to tackle with deep reinforcement learning, let me give you some background on API testing. So the basic flow of testing an API goes a little bit like this. A tester sends a request to an API, the API gives a response, and finally the tester evaluates that response. Now, of course, we don't want a human tester to do all of this work manually. So we need a way to automatically generate these requests and evaluate the responses. This is where the OpenAPI specification comes in. This handy specification, which is used by many RESTful web APIs, contains a lot of information. By looking at the paths and components parts of this specification, we have enough information to generate API requests along with their parameters. And there's even information that we can use to evaluate the response of the API. So now you might be thinking, okay, that seems easy enough, but there's a catch. Generating individual requests and sending them to the API is not enough. Imagine we have an API for a cloud computing service, and the API request that we want to test for is called delete snapshot. We could just send this request to the API and observe the response, but surely if there's no snapshot to delete, we will not be testing the actual intended functionality of the API request. If we want to evaluate the intended functionality, we should probably first send the request create snapshot and then use the ID of the created snapshot as an input parameter for delete snapshot. So when we're generating test data for an API, we want to generate these sequences of API requests. We can do this with a scenario-based approach. On top of the OpenAPI specification, we defined scenarios that specify the usage flow of API requests. On the left is an example of one individual scenario, and on the right is a more graphical representation of that scenario. Dependencies, such as this one, are used to link the input and output parameters of different requests. These scenarios can be created manually, but you might also imagine that we could easily infer such a scenario from API usage logs. If we take all of the individual scenarios together, then we can combine them like this into one large scenario model graph. And using that scenario model, we can then start to generate valid sequences of API requests by traversing the graph and satisfying the dependencies. Okay, so here comes the big challenge that we want to tackle with reinforcement learning. Scalability. So there are two sides to this. First, there are the resources that are required for executing a test suite, and then the time required for generating that test suite. Now you can imagine that the request from our previous example, create snapshot, takes a lot of time and resources to execute, seeing as it clones a complete virtual disk into an image, right? If at all possible, we don't want to execute this request too often. And as for the other side of scalability, we simply don't want to wait for days before a decent test suite is generated. So here comes the interesting part. With SBST, it's quite common to decide on a fragment of code that we want to reach, and then search for the input parameters that allow us to do so. So in our case, that would mean choosing which API request to generate, and then searching for a path in the scenario model that passes it, while satisfying all the required dependencies and constraints. Let's say, for example, that all these requests with red dots have already been covered. Then we would simply select an uncovered request, such as this one, and find a path that passes it. Maybe something like this. And I'm drawing this now based on the lines, but I'm actually not sure if this path would satisfy all of the constraints as they are hidden in this simplified graph. Okay, so this is a possibility, right? But this approach doesn't give us any control over how big the test suite becomes in order to reach 100% coverage. Because we just keep generating sequences until we reach this criteria, right? So what we wanted to do was to take it a step further and search for a complete test suite in one go. This way we could specify that we want to optimize the coverage of requests and the coverage of all the transitions between requests, while limiting the total number of requests in the test suite. So for example, we could say, give us a test suite with 200 API requests in total, and then maximize the request and transition coverage. This is something that we managed to accomplish with deep reinforcement learning, but it did require a smart approach. All of these transitions can have multiple conditions as the result of the dependencies between request parameters. So while generating a sequence of API requests, there are strict rules to follow. And that's when I found this wonderful paper by Feldt, who is also giving a keynote for the SBST workshop this year, and Simon Poulding. Now, if this were a real-life presentation, I would probably ask how many of you have read the paper, but for this video I will just assume that some of you raised your hands and some of you didn't. So Feldt and Poulding proposed a framework for generating collections of well-structured data that exert certain properties. Their basic idea was to make a clear separation between the generation of structured data and the optimization of specific properties of that data. So they do this by introducing a construct which they call choice points. A choice point can be used by generator programs such as our API request sequence generator in order to add non-determinism to the program. So for example, let's say our generator has already generated a couple of API requests and wants to determine which API request to generate next for the current sequence. It first determines which transitions are possible given the constraints and the previously generated API requests, and then it uses a choice point to choose from the final list of options. As far as the generator is concerned, that decision is totally stochastic, but in the background the choice model is making the decision. In their original paper, Feldt and Poulding proposed a stochastic sampler-based model. A search algorithm can tune the parameters of those samplers in order to introduce a certain bias in the generated data. The basic principle of their approach is that generator programs make use of decisions that are made by an external party, namely the choice model. And this is exactly what happens in reinforcement learning as well, seeing as reinforcement learning is fundamentally about optimizing sequential decision processes. But then in reinforcement learning, the generator program is called an environment, the choice model is called an agent, the choices are called actions, and the fitness is the sum of accumulated rewards. Feldt and Poulding even mentioned themselves that they envision adaptive learners as choice model. So that's basically what we did. This is a general overview of the framework that we made. So on the left we see the stuff that I talked about earlier, right? The OpenAPI specification and the scenario model. These are used by the generator for sticking to the rules of generating valid test data. And then on the right we see how the generator relates to the choice model. Now, originally, Feldt and Poulding used the sampler-based choice model, and we replaced that with an alternative reinforcement learning-based choice model. We do so through the very popular OpenAI GYM environment, which allows us to easily apply any reinforcement learning algorithm. So here I would like to take a moment to highlight the biggest benefit of reinforcement learning over conventional search algorithms. Normally, with search algorithms, we generate some data, so this could be either input parameters or, in the case of the sampler-based choice model, the parameters of the samplers. And then we look at the fitness of that generated data, and depending on the actual search algorithm we're using, we take some steps to generate data with a better fitness at the next iteration of the search. With reinforcement learning, there's an addition to this. Each time the reinforcement learning agent has to make a decision, it first makes an observation of the current state. And to give a better understanding of what this state is, I'll give another example with our scenario model. So this is our scenario model, right? The generator is right in the middle of generating a collection of request sequences, a test suite. And the red dots mark the requests that have already been covered. So let's zoom in a bit. This API request marked with a blue circle is the request that was generated last. So it's the current position on the scenario graph. And the agent now has three choices, right? It can either go here, here, or here. But before the agent makes the decision, it first looks at the state. And this state is actually exactly what we are looking at right now. The first part is simply its position on the graph, so the agent knows that it's here right now. The second part is which requests have already been covered by the previously generated request sequences. In other words, the agent can see the red dots on the graph. And for simplicity, we left it out here, but the third part of the state is which transitions have been covered. So now, given this state information, the agent knows that ahead of it there are still two requests that have not been covered yet. So if it's been trained well, it will choose this path, right? And then this path to obtain not one, but two rewards for covering new, previously uncovered requests. If the agent did not have any of this state information, it would have had no way to make such an informed decision. So this is why a reinforcement learning based approach allows you to give so much more control out of hand to the search algorithm. And this example might seem trivial, but besides following a path indicated by arrows, the agent also has to make sure that all the required transition constraints are satisfied, making the decision process much more complicated. So I've been talking a lot, but you want to see results, right? Well, when we wrote the paper, we didn't actually have any experimental results yet, and we just argued the benefits of a deep reinforcement learning based approach. But in the meantime, we've made a proof of concept implementation of the framework, and we've run some experiments. We used A3C, or Asynchronous Advantage Actor Critic, as reinforcement learning algorithm for our reinforcement learning based choice model. And we used a genetic algorithm and random search to compare our approach to the sampler-based choice model. This chart shows the best fitness value at each point in time during the search. The overall fitness is calculated as 2 times the request coverage plus 1 times the transition coverage. And each line is the average of 3 runs. We can clearly see that the reinforcement learning based approach in combination with the A3C algorithm has a major advantage in this context. Now, these results don't mean that the genetic algorithm can't find the optimal parameters for the samplers. In fact, it clearly outperforms random search. Our reinforcement learning-based approach, however, is so fundamentally different that it can achieve another level of results compared to the sampler-based approach. So now that we have looked at this example of API test data generation with reinforcement learning, I encourage you to also rethink the depth of automation that could be achieved if you were to apply a smart deep reinforcement learning algorithm to your own testing challenges. The framework of Feldt and Poulding is very flexible. You can use it to generate any type of structured data or easily formulate any kind of decision process. By then applying deep reinforcement learning to use as choice model and by clearly describing the required state information, you can set complicated optimization requirements and still obtain good results.